Okay, in this second part of horizontal projectiles, we're going to look at the displacements and the components and how to track the motion as we go. Okay, in number 5, we have again the horizontal cannon shooting the projectile over a level surface, and you can see the path that it takes. Again, that is a parabolic trajectory. The initial velocity is only in the x, not in the y, so we don't have any upward or downward component of the velocity. Now, the first thing we want to do is figure out the horizontal and vertical displacement after the 5th second. So the first ball is 0 seconds, so the 5th one after that is 5 seconds. Again, displacement is the straight line from where you started to where you finish. Now, if I was to get the overall displacement of the ball, then I would be looking at from here's where I started, here's where I finished. That would be the overall displacement. Now, any vector can be broken down into two perpendicular components, and in projectiles we like to do that a lot because we have an x dimension and a y dimension, and they are different from each other. So if we want to look at the x dimension displacement, here's where we started in the x, and here is where we finished in the x. So the green arrow would be our x displacement. And then if we want to know where we went to in the y direction, we started at 0 and we went down to where the ball is now. So that would be our vertical displacement. Now we can see from the graphic that it looks like 250 meters for the horizontal displacement and 125 meters for the vertical displacement. We could have predicted the vertical displacement. It's 5 seconds later. Delta y is going to be the distance in the y direction. Would be ut. It would be u in the y times t plus 1/2 gt squared, since the acceleration in the vertical dimension is g. There is no initial velocity in the y, so that part cancels out. 1/2 of g is 1/2 of 10, which is 5 meters per second squared, times the time squared, 5 seconds. Second squared cancel out. 5 times 5 times 5 is 125 meters. We've already seen that multiple times. Now, if we had known what the initial velocity was in the horizontal, we could have predicted that it would be 250 meters. Now that we know that it is 250 meters, and that took 5 seconds, then we could expect that the velocity of the ball in the x direction would have been 250 divided by 5, which is 50 meters for every second. Now, that ux, again, stays constant. There are no forces in that direction. Summation of forces are 0, so the velocity in the x dimension stays constant. We can see that if in this next one we track the motion at different points and write down the velocities. Here we're starting at 20 meters per second in the horizontal direction. Again, there are no forces in the x direction. Therefore, whatever the initial velocity in the x is the velocity in the x at all points in time. So if it starts at 20 meters per second, at all points of time, it will be 20 meters per second. No change. We're assuming no air resistance, so no slowing from that. There is no forward force. The object is moving in the horizontal only because of inertia. So a projectile travels forward because of inertia and is pulled downward by gravity. Now, since we are being pulled down by gravity, the acceleration rate will be g. If I round that off from 9.8 to 10 meters per second for every second that I fall, essentially my new velocity in the y direction will be the acceleration rate of g multiplied by the time that I fall. After 1 second, 1 times 10 is 10. After 2 seconds, 2 times 10 is 20. 3 seconds, I'm going to be at 30. And 4 seconds, I'm going to be at 40. So I'm just increasing my speed by 10 meters per second for every second that I fall in the vertical. Again, you should know there's no vertical velocity vector there. This is the 10 meter per second velocity vector in the vertical. Now it's 20, twice as long, now 30. So you can see the vertical velocities are getting longer, while at the same time the horizontal velocities are staying the same. So the horizontal velocity, no forces in the horizontal, therefore the forces add up to 0. There are no forces based on our assumptions, therefore it doesn't change. In the vertical, gravity causes it to increase at the rate of 10, or 9.8 more precisely, meters per second for every second that it falls. Okay, if it hits the ground 4 seconds later, if each of those dots is 1 second apart, the first question is, how high is the cliff? Now, height would be a vertical question, so we'd be looking at what is the change in the y direction. Again, that's going to be based off of u, y, t, plus 1/2 g, that's the acceleration in the vertical, t squared. There is no velocity in the y direction, so again, it's 1/2 gt squared. So 1/2 of 10 is 5. And we multiply that by 4 squared. Second squared cancel out. 4 squared is 16. 16 times 5 is going to be 80 meters. So the cliff height must have been 80 meters for the ball to fall, to hit the ground 4 seconds later. How far from the base of the cliff will it land? That's an S in the x direction, a horizontal question. Again, in the x direction, I would start with the same basic equation, the velocity in the x times t, plus 1/2 of the acceleration rate in the x times t squared. But I should right away realize there is no acceleration in the x direction, so the velocity stays constant. So the distance I travel is just how fast I was going, 20 meters per second, multiplied by the time that it took, 4 seconds. Seconds do cancel out. I'm left again with 80 meters. So in this particular case, number 6, the object would have traveled outward 80 meters and downward 80 meters. If we wanted the overall displacement, we could use Pythagorean theorem and add up 80 in the horizontal plus 80 in the vertical, and 80 squared plus 80 squared, take the square root, and we could figure out the overall displacement of the object, and we get about 113 overall meters, 113, roughly 110 to two significant figures. Okay, that's displacements. I wouldn't add, and we could also add velocities like that, and we could figure out the total velocity of the object at the time it got finished. It would have been moving 20 meters per second and downward at 40 meters per second. So we could do 20 squared plus 40 squared and then take the square root of the answer and get 44 meters per second. Now that's only the magnitude of the velocity. We could also figure out the angle at which it was by using cosine, sine, or tangent of the particular velocity triangle. Well, we'll leave that for another time. Okay, if we change the initial speed in question number 6 to 16, okay, the only change would be the how far the object went in the x direction. It would still take 4 seconds to fall. The fall time is based not on where it lands, but how much time, how high it's projected from. Therefore, that will determine the time that it takes to hit the ground. By increasing s of x, by increasing the horizontal velocity, now to find how far we've traveled, we'll multiply decreasing the horizontal this time. We've gone from 20 down to 16. 16 meters per second times 4 seconds, and we won't travel as far. We'll only travel 64 instead of 80 meters. So if we project it slower, it does not take less time in the air. It simply will not go outward as far from the projected height. Cliff, desk edge, table edge, whatever it may be. Okay? So the two axes are independent of each other. I did not have to go back and recalculate SY or go back and recalculate the time to fall. Those are exactly the same. All right, so that's how we deal with horizontal projectiles. X direction is simply a constant velocity case, and the vertical direction, we have the acceleration due to gravity, so it's an accelerated case.